Okay, thank you for your introductions. And in this presentation, I'll be talking about the dynamics integration of large-scale brain network during memory encoding. Previous imaging studies have shown that activations of specific state of brain regions are predictive of memory encoding performance. More recently, it has been shown that memory encoding is related to enhanced functional connectivity or FC between the memory-related regions. But memory encoding is thought to require many brain systems beyond the memory system because encoding success depends on a range of factors. Most previous studies have examined FC from a few selected state regions, providing little evidence on how the entire brain functions as a network to support memory encoding. Notably, recent studies have revealed that large-scale brain network dynamically fluctuate typically within a time scale of 30 to 40 seconds. Furthermore, dynamic fluctuation of large-scale FC patterns are associated with a variety of cognitive processes, leading researchers to focus more on time-varying FC patterns instead of traditional static FC computed in longer time periods. In the present study, we explore whether and how dynamics integration in large-scale network across the brain are related to fluctuations in memory encoding performance. 25 university students participated in this study. We used multi-band EPI sequence to obtain functional data. The participants took part in 2 sessions: experiment and incidental encoding task, followed by a surprise memory test. In the incidental encoding task, we presented 360 pictorial trials to the participants during the fMRI scanning. They judged whether the object on pictures is man-made or natural. 20 minutes later, the participants performed the surprise memory test. They answered that they recognized its picture with high confidence, low confidence, or that they believe that this is the new pictures. According to this procedure, we can classify the encoding trials into high confidence hit, low or HH, low confidence hit or LH, and missed trials. Next, we investigated the dynamic FC of large-scale brain network during the encoding phase. We defined 224 ROIs derived from the power as large and extracted signal time cost from each ROI. To relate the dynamic FC to encoding performance, we divided the fMRI time series into non-overlapping small time windows. Each window consisted of 50 TR or 36 seconds. Then we classify the time window into 2 groups based on encoding performance, according to the proportion of HH trial for each window. And then we calculated the correlation coefficients across all ROI for each time window, and then average across the high encoding state and low encoding state. Here are the correlation matrix of high and low encoding stage. These 2 FC patterns look quite similar. However, by comparing the correlation matrix of high and low encoding stage, we observe significant difference in FC associated with encoding performance. The left panel indicates the significant difference in FC between the states. The upper diagonal part shows connections with significant difference, which are illustrated in the right panel. The top right panel illustrates 98 connections showing significant FC increase during the high encoding state, whereas the bottom illustrates 687 connections showing significant decrease. More specifically, the high encoding state is characterized by an increased long-range connections. In contrast, the low encoding state appear to be characterized by increased local connectivity among neighboring regions. When we calculated the Euclidean distance, the straight line of each pair of ROI was significantly longer in high encoding state. This is interesting because it may indicate that the brain shows different levels of network integration and segregation depending on encoding performance. To test this possibility, we apply graph theory to our data. Theoretically, integration is important for efficient communication across entire system, and segregation is critical for specialized functioning of particular module without interference from the rest of the network. First, we computed global efficiency, a measure of integration defined for entire network, and local efficiency, a measure of segregation. We found that global efficiency was significantly higher during the high encoding state, whereas local efficiency was not significant difference. We next computed the participation coefficients, or PC, and local efficiency for each subnetwork as a measure of integrations and segregation respectively. We found higher PC during the high encoding state in two subnetworks, subcortical network and salience network. However, when we examine the subnetwork-wise local efficiency, we didn't observe the significant difference for each subnetwork separately in any specific subnetwork. We next investigated whether any specific pair of subnetwork drove this network integration during the high encoding state. To this end, we defined inter-subnetwork efficiency, which quantify the integrations between each subnetwork pair. We observed higher inter-subnetwork efficiency during the high encoding state, particularly in subcortical network, salience, default mode, and visual network. Finally, we perform a cross-subject binary classification using support vector machines, or SVM. We use a set of graph metrics, subnetwork-wise PC, subnetwork-wise local efficiency, and inter-subnetwork efficiency as input of the SVM to classify high and low encoding state. The SVM can reliably predict the encoding state with significant classification accuracy when we use the graph metric defined as a subnetwork level. This result indicates that the graph metric can reliably represent the large-scale brain network of memory encoding. To check the specificity of our findings, we perform two control analysis. This time, we classify the time window based on the number of pictures or average reaction time computed within each window. In these two control analysis, we didn't observe the significant classification accuracy. Okay, just a quick summary. We demonstrated the dynamic reconfigurations of large-scale functional brain network associated with temporal fluctuations in encoding performance. Specifically, we observed a high level of network integration in periods of high encoding performance. And this effect was mainly driven by increased inter-subnetwork integrations of the subcortical default mode, salience, and visual subnetwork with other subnetwork. And if you need more detail of our work, you can visit our poster today or tomorrow, number 2127. And I would like to thank you my colleagues and thank you for your attention. Thank you so much.